A regional bank deploys a machine learning model that determines credit line adjustments for existing customers. The model passes the governance committee review. The committee spent the previous year building a robust AI governance framework focused on language model risks, including content filters, output monitoring, prompt injection prevention, and hallucination detection. The credit model is not a language model, but the governance framework is the only one the committee has, so they apply it. 18 months later, the fair lending audit reveals that the model has systemically reduced credit lines for customers in specific zip codes at rates that correlate with protected class characteristics. The model never generated inappropriate content. No prompt injection occurred. No hallucination was detected. The government's framework monitored everything it was designed to monitor and missed the only thing that mattered. $3 million in regulatory fines and a consent decree later, the bank built the second governance framework. They should have built that one first. This is Machine Learning Governance is not LLM Governance. ML, Part 31. Why the framework that governs your language model will miss every failure mode that matters in your machine learning system. Section 1. What machine learning governance actually governs. Machine learning governance manages risks that are statistical, gradual, and invisible to any observer who is not specifically looking for them. Model performance degradation is the defining machine learning governance risk. A fraud detection model trained on transaction patterns from 18 months ago begins to miss attack vectors that emerged 6 months ago. Accuracy drops from 94% to 71% over 2 quarters. The model keeps running. Predictions keep flowing. The degradation is invisible to anyone not monitoring the statistical relationship between predictions and outcomes over time. By the time financial losses reveal the problem, the damage is accumulated for months. This is concept drift from Part 12, expressed as a governance failure. Monitoring infrastructure detected early is not optimal sophistication. It is the core of machine learning governance. Data quality failures compound performance degradation in ways that are harder to detect because they occur upstream of the model. A feature pipeline that be receiving malformed input does not fail loudly. It produces predictions from garbage data with the same confidence it scores it produced from clean data. The model has no mechanism to distinguish. Data governance that validates inputs against expected distributions and large flag anomalies before they reach the model is the difference between catching a pipeline failure in hours and discovering it in a quarterly audit. Fairness and bias monitoring is where machine learning governance intersects most directly with regulatory risk. The bank in the opening scenario was not running a biased model by design. It was running a model that learned spurious correlations between zip codes and creditworthiness from historical data that reflected decades of discriminatory lending practices. The model was optimized for the pattern in the data. The pattern in the data was discriminatory. Fairness governance that continuously monitors prediction distributions across protected class proxies catches this before the regulator does. Section 2. What LLM governance actually governs. Language model governance manages risks that are immediate, visible, and quantitatively different from anything in the machine learning governance framework. Content safety is the primary domain of LLM governance. A language model that generates instructions for harmful activities, produces discriminatory content, or outputs information that creates direct safety risks, fails in ways that are instantly visible to the user who receives the output. The failure is not statistical, it's categorical. The response is either safe or it is not. Governance frameworks that focus on content filtering, output classification, and red team adversarial testing address this failure mode directly. Hallucination management is the LLM governance challenge that has no analog in traditional machine learning governance. A language model generates plausible, confident, grammatically correct statements that are factually wrong. The model does not know it's wrong. The confidence of the output gives no signal about its accuracy. Governance frameworks that treat language model outputs as requiring source attribution, factual verification, and human review for high-stakes claims addresses a failure mode that does not exist in the same form for prediction models. The risk profile difference matters because the two failure modes require different detection infrastructure, different remediation approaches, and different organizational ownership. Machine learning failures require statisticians to monitor performance metrics. LLM failures require content reviewers to monitor output quality. These are different skills, different tools, and different processes. A governance framework that conflates them provides neither effectively. Section 3, the third domain, semantic governance. In systems that combine machine learning pipelines with knowledge graph infrastructure, a third governance domain emerges that neither machine learning governance or LLM governance addresses. The knowledge graph is not passive infrastructure. It actively shapes machine learning outputs through ground element, the mechanisms we examined in Part 22. An ontology rule that fires incorrectly propagates through every downstream inference that depends on it. An assertion that enters the knowledge graph without validation poisons every prediction grounded in it. A provenance chain with gaps produces audit failures at exactly the moment compliance review requires a complete record. The semantic governance asks questions that neither machine learning governance nor LLM governance frameworks were designed to answer. Who is accountable when an entailment rule produces an incorrect inference that drives a consequential automated decision? Who validates new assertions before they enter the certified knowledge layer? Who owns the ontology as the domain it describes evolves? How frequently does the knowledge graph require freshness audits to ensure that the grounded facts still reflect operational reality? These are not hypothetical governance gaps. They are the gaps that surface when a program office asks why a machine learning system made a specific recommendation, and the answer required tracing through a knowledge graph whose governance was never formally defined. The provenance infrastructure from Part 23 makes the trace possible. Semantic governance is what ensures the trace leads somewhere accountable. Section 4, where the frameworks must work together. The bank's credit model failure was simultaneously a machine learning governance failure, a fairness monitoring gap, and a semantic governance failure. The model's feature definitions connected to data sources whose terminology was never formally reconciled against the fair lending ontology that the compliance team used to evaluate discriminatory patterns. The machine learning governance framework monitored model accuracy. The LLM governance framework monitored content safety. Neither framework asked whether the concepts the model reasoned over were formally defined in terms that compliance review would independently verify. Organizations building AI governance frameworks that treat all systems identically are not governing AI. They are creating documentation that satisfies approval processes while leaving the actual risk landscape unmonitored. The monitoring infrastructure that detects machine learning performance degradation does not detect LLM content failures. The content moderation system that catches inappropriate language model outputs do not detect credit model bias. The provenance tracking that makes knowledge graph assertions audible does not exist by default in either framework. Effective governance maps risk profiles to oversight mechanisms rather than applying a single framework to every system type. Machine learning systems need performance monitoring, data quality validation, fairness audits, and operational reliability controls. Language model systems need content safety infrastructure, hallucination management, and usage boundary enforcement. Semantic infrastructure needs ontology governance, assertion validation, entailment rule auditing, and knowledge freshness monitoring. The principles of transparency, accountability, and risk management apply consistently across all three. The technical implications of those principles do not. Section 5, why this matters. The governance framework built for the AI system you deployed first will be applied to every AI system you deploy next, unless someone explicitly prevents it. That is not a failure of intention. It is a failure of recognition that different AI technologies have genuinely different risk profiles that require generally different oversight mechanisms. The organizations that get this right build governance frameworks before they build systems, map risk profiles to oversight mechanisms for each system type they operate, and treat semantic infrastructure governance with the same rigor they apply to model versioning and data quality. The organizations that get this wrong discover their governance gaps the same way the bank did in a regulatory examination after the damage is done. In Part 32, we will discuss explainability in production machine learning, why understanding predictions matters as much as accuracy, and why the semantic layer gives explainability something it has always lacked, or formal vocabulary for describing what a model actually reasoned over.